Every algorithm has its own properties. Some are more efficient than others. We will go over time complexity in another lecture, but right now let's go over some common algorithms and their properties. Here's an insertion sort. In the best case scenario, it will only take n passes to sort an array, where n is the size of the input. Average and worst case scenario, it will take n square passes to sort. Here's a shell sort. In the best case scenario, it'll only take n passes to sort an array this way. Average and worst case scenarios, it'll take the square of n times log n. The quick sort uses recursion to iterate over all of the items in the array. In the best and average cases, the sort will take n times log n passes, and at worst case it will take n squared passes. These sort algorithms work with array structures, where the data is in a linear format. We can store data in trees as well, and a binary tree structure will make it easier to keep data sorted every time something is inserted, instead of having to sort it after the fact. But even if a tree is sorted, we still need algorithms for finding data within that structure. How do you traverse a tree efficiently? If we were traversing a tree to output the nodes, or even to search it, what order would we go in? We could display the nodes in order by their values. We could display the nodes in pre-order, outputting each node before going to its left and then right child recursively. We could display the nodes in post-order, visiting each node's left and right children recursively before outputting the node itself. Or we could take a breadth-first traversal approach, where we display each node of one level at a time, going from top down. We can use these different traversal strategies to search for data within our tree. We could get really in-depth into these algorithms, but usually there's an entire course dedicated to data structures and algorithm analysis, so we're just going to deal with some basics. Think of this more as an introduction. Let's implement a binary tree and work with depth-first traversal and searching. Alright, so for a binary tree, we're going to have a tree object and a node object. A node will store its contents as well as a pointer to a left and a right node. So, we have to create a node, class node. We will have a constructor, a destructor, and whatever the value is. So we can either make this private and have it be a friend of the binary tree, or we can make it public. Let's just go ahead and make this all public, just kind of treat it like a struct. We'll store integer values, we'll have some value, and we'll have pointers to the left and right nodes. Okay, so over here we will create these functions in the constructor. We're going to initialize the pointers to null. And if we want to set a default value, we can. That's not really needed. Let's have node destructor. And what this will do is it will destroy each of its children. So when the node itself is being destroyed, it will then in turn destroy its children. So if the pointer to the left is not pointing to null, and if the pointer to the right is not pointing to null, then we'll tell it to delete whatever's at that space and set pointer left to null. So it's very important to keep your pointers set to null if they are not pointing to anything, if you've freed that memory or otherwise have not initialized them. That way we can have a good way to check to see if we've initialized some memory that we need to get rid of. So this is a basic node. Then our binary tree will contain the first node as well as functions for inserting and searching and all of that. Alright, for the binary tree itself, we will need some constructors, or just one constructor, a destructor. Probably want something like an insert function that maybe will return true or false if it was successful. The data type we're dealing with is integer, so we'll just pass in an integer value. we'll have a search. So we'll search to see if some value is in the tree. And we'll have a starting node, the pointer to the root. So if I open this, again, the tree itself is only storing a pointer to this, and then each node keeps track of who its children are. Now, we're passing in an integer value here because from the user's standpoint, they just have a tree and they just want to insert integer values into it. So they don't care that there's a node behind the scenes, they just know that they're dealing with integers. And later on we can also rewrite this so that we can store any type of data type in here, but we haven't gotten to that lecture yet, so we're not. Alright, over here, binary tree. Again, we want to set our pointer to null initially, and for the destructor, we are going to see if the root is null or not, and if it's not null, we're going to delete it and set it to null. So when the binary tree itself goes out of scope at the end of the program, then it will call the destructor. It will check to see if the root is pointing to anything. If it is, it'll free that memory, then it will be destroyed, so the node's destructor will be called. It will call its left and right pointers to be destroyed, then their destructors will be called, so it will continue going downwards. Okay, so let's do an insert. We'll have Boolean, it'll return either true or false if it's a success or failure, binary tree insert, and some value. Now, if the list is empty, if the tree itself is empty, it's easy. We just say the root is this value. We're going to create a new node. I don't have a constructor that takes that, so we'll say new node value is equal to the value that's passed in. And if the root is not pointing to any address, we're going to point it to that new node. Now, I know it's good practice to get into the habit of writing a delete every time you see a new, but in this case we aren't going to do that. We don't want to delete the information after we're done inserting. It's going to be the root, or it's going to be somewhere in the tree, and the destructor itself will take care of all of the deletes. So don't worry about putting a delete in here. Now, this will work if the tree is empty. But what about if the tree has some nodes in there? We need to find a location. Well, we're going to have to traverse through everything. So say we wanted to insert a 6. We'd start at the root. We'd say, okay, well, 6 is less than 7, so we'll go left. 6 is greater than 3, so we're going to go right. 6 is greater than 4, we'll go right. 6 is greater than 5. There is no child to the right of 5, so we know that our 6 will go here. So, in order to find a position in the tree, we'll have to keep track of who the parent is, and we're going to just go through all of the nodes in order. Not all of the nodes, but in the path that we went over. So we'll have to keep track of the parent, because by the time we are pointing at where this new node should go, we might not have the parent anymore. So let's just do this. So while true, we're just going to traverse the tree. We will set the parent, pointer parent to pointer current, and then we're going to move current along. So first we want to make sure that there are no duplicates, at least for this tree. If there's a duplicate, we will be able to see if this node has the same value as the value of the new node we just created. If it does, we don't want it. So if the value that was passed in is equal to the value of the current node that we're looking at, then we're just kind of going to undo what we did. We're going to delete our new node and return false. Okay, so we don't want any duplicates, only one of each value. Otherwise, we're going to look at, is the value less than what the current pointer's value is? So again, 6, if we're inserting a 6, it's less than 7, so we're going to go left. If it were greater than 7, we would go right. So we're going to move left for here, or otherwise we're going to move right. So if the value is greater than, we're going to move right. Now this could be an else statement. I kind of like having it as a else if, just because it looks nicer. Otherwise we can also just move this duplicates down here and say, well, else we don't want any duplicates. Oops, I'm missing a curly brace. So it's either going to be less than, greater than, or equal to. Alright. So if we're going to move left, we can say pointer current is equal to pointer current to the left. Is that correct for the node? Pointer left. Okay. And if pointer current is null, then we can say the pointer parent left pointer is equal to this new node, and we can return true. Now, I wrote my example code for this last night at like 1 AM, so this is a little bit redundant. Instead of doing this, we could just say if pointer current to the left is equal to null, then we would set the pointer current left pointer to new node and not have to deal with this part. So let's get rid of that. Make sure that builds. And it doesn't like the null. If you're getting an error that null was not declared, it's because it was honestly declared in the standard library. It's not actually a thing in C++, as far as I know. So you have to do that, or you have to include some library to get null. Though, I got some other stuff to deal with. This could also be null pointer, but I'm just kind of used to using null, even though I need to stop that. Okay, pointer parent, we don't need that anymore. Okay, so if we're moving left, if the current pointer to the left is null, we're going to set that there. Otherwise, we're going to want to move left. So pointer current is equal to pointer current and pointer left. So then we can also basically use this for the right side. We want pointer right. Build. It says it reaches the end of the non-void function. That's just because, well, it's going to be in this while loop, and it's going to, I guess there could maybe possibly be an infinite loop, but I don't know. It should either hit a duplicate or it should find a position in the tree. But this is just a warning. We could kind of like put some dummy thing here, but it's shouldn't get to this point because we have an if and an else and then a loop. But I don't really like having code that is not actually supposed to do anything. I'll just go with the warning for now. Okay, so we have tree, insert 4, 6, 7, 9. Let's make sure it builds and runs. Now it's not telling us anything, so we could just output some information. So insert value, and then for every item that we're looking at, let's say node, and we'll say its value just so we can kind of get an idea. And that's really hard to read, so let's also add an end line. Oops. So insert 4, it just went to the root. Insert 6, it looks at 4. Insert 7, it goes to 4, then to 6, and so on. It's not very graphically nice, but it's kind of hard to do really sophisticated stuff with just the black and white ASCII characters and not really much control over the screen. Okay, so this is our insert function. It's either going to be at the root node, or we're going to have to look for a location and traverse through the tree. Okay, what about search? Alright, so when implementing the search function, there are a few ways we can decide to traverse this. So I'm going to create a few different functions here, and we'll just switch between them. Let's have a pre-order search. We're going to pass it in a node and the value we're searching for. Sorry, this is a little hard to see. There we go. We'll have a post-order search and an in-order search. These are all depth first style. Depth first. So I will define these down here, but basically if we start with one of these, we can say return whatever this is going to return for us, and we'll start looking from the root node. So pointer root, and we're looking for that value. Now for each of these will be recursive, so if they don't find the value at the root, they're going to go to the left and right children to try to find it. So pre-order search, the way this is handled is basically you'll have check current value, then go left and right. For post order, it would be go left and right, then check current value, and for in order, you can say check left, then value, then right. Though this might be a little bit better for when we're actually displaying these numbers, and we can write a display function too. So, but this is just an example of how this would be traversed. So for pre-order, if the pointer node that was passed in is null, then we're going to return false, because that means at some point we've gotten to the end of the tree, or we were passed in some bad value. Otherwise, for the pointer, if the value is equal to what we're searching for, we're going to return true. And otherwise, we're going to return whether the left or the right node has that value. So let's say we return pre-order the left node, searching for the value, or pre-order the right node, searching for the value. So we can return it this way. And pre-order search. Okay. So we can also write some functions for like displaying in different orders. So void display pre-order, we just need a node, post order, and in order. And these will be kind of similar. So let's do this. Binary tree, so if we're going to display everything, let's say void display, we would say cout, the pointer node value, and then we can also just say display pre-order for its children. And while I'm at it, let's do that down here. We'll display the children first and then the item, and then here we display the actual value in between the left and right children. So let me go ahead and implement this display function real quick. We can display pre-order, post-order, actually let's make these all on the same lines. We'll have in order. And we will get rid of these end lines here as well, just so they'll all be on the same line. So we can then say pre-order, display pre-order from the root node, display post-order, and display in order. I'm going to comment this out for a moment, and let's just say tree.display, and it will show us the different ways it will be displayed. And I got a segmentation fault. Let's see if the debugger will tell me where it's getting that. We are display pre-order. Okay, I'm not checking to see if it's void first, so, or not void, sorry, I meant null. We'll just return. Okay, so pre-order, post-order, in order. Okay, yeah, we only have 4 items. So in order is in the actual like numerical or alphabetical order if we had it as an alphabet. Post order and pre-order. Let's see, that's in order. Pre-order, it goes to its children first and then to the node itself. Post order, it goes, oh wait, sorry, I have that backwards. It goes to the value first and then to the children, and for post order, well, it doesn't work right if I don't display it correctly. There. Post order, display both the children and then the value. Pre-order, display the value and then both the children. Okay. Okay, and back to searching. Let's just do something similar to this, where we'll actually just display the result. Search for each of these. Now it'll return a boolean, so we can just output the boolean value. And this will be the pre-order search, the post-order search, in-order search, and we're searching for each value. And then, since it has to return a boolean, we'll just return one of these. Okay. So this one is checking the value and then checking left and right. This one will check the left and right and then check the value. So for the post order search, if post order search for pointer node, pointer left, value, or post order search for pointer nodes right, right, value, then we can return true, because one of those is true. Otherwise, if pointer node value is equal to the value, we can also return true, or we can return false. And down here, we can say, oops, if in order search, pointer node to the left, then we're going to return true. Or we can check the value itself, or we can check the right side. And if all of those failed, we're going to just return false. Okay, so when I run this, and we're searching for 7 and 8, 111, 0, 0, 0. Now this doesn't illustrate a whole lot, so rather than having these, let's see, pointer node value value, let's have just a simple function so we can display everything. So node equal has value, I don't know, what's a good name? Pointer node and the value. This will just be a shortcut for us. I'll put this up here. And basically we're just going to use this so we can display the pointer node's value that we're currently looking at. And then return pointer node value is equal to value. So instead of doing this, we can do this for the pointer node and the value, and that should just display each one as we're going. So I'm going to replace all of these, and if I run this, let me see, pre-order search, and then it's not really showing us a very good whether it's true or false. So let's see, bool found, can just say if found, then cout found. And read declaration. Okay, so pre-order search. This is 467 found, 97 found, 467 found. Do I have these all correct? We have pre-order, post-order, and in order. So let's see, 467. Everything's all kind of jumbled now, so it's harder for me to read. We have pre-order traversal 4679, 97, and then 4679. Okay, and we have the other search for an 8. It goes through 4679, 9764. Oh, this is just occurring twice because I'm returning this at the end, so that's why those two things are there. So we could just return found instead. Oh, what? Q? Oh, accidentally typed that. And so we have found, 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 blah, blah, blah. And it shows you the way it was traversing in order to find those values. Ooh, let me close that. Okay.